Hi, everybody. Welcome to now our 8th lecture in CHY 113 and our first lecture of Unit 2. Starting to really get into some meat of some things now. And so since we don't have any review questions from last time, since you just took your test, let's go ahead and just dive right in. And so let's take a look first at where we've been. Let's just go through what we looked at in Unit 1. So we started out by talking about some of the basic tools of chemistry, some of how we deal with numbers, things like significant figures and scientific notation, the metric system. From there, we moved into basic atomic structure. We looked at the different parts of an atom and how we can then use the things like atomic number to figure out ions and what sorts of ions compounds might form. We talked about chemical formulas, how are elements going to come together into various compounds and in what ratios will they do so. Talked about how we can name chemical compounds, the different rules involved with that, depending on what type of compound it is. We discussed how to convert using moles and looking at the amounts of chemicals that way, looking at grams to moles, for instance, and numbers of atoms using Avogadro's number. And then finally, we finished Unit 1 with a discussion of an introduction to chemical reactions and how we can depict reactions in chemical equations, balancing chemical equations, and the types of equations and reactions, and some details about how we write those. Now, I point this out and I talk about where we've been and what we've done, because what we're going to be moving into now in Unit 2 really is going to build off these things. If you are having trouble, for instance, still, if you haven't really mastered your mole conversions and being able to convert back and forth between grams and moles and using Avogadro's number to calculate the number of atoms, if you're having trouble balancing chemical reactions and figuring out the products of chemical reactions, those are all things that we are going to be using in Unit 2. And so I bring that up just so to point out that if you are still struggling with some of that, if you haven't quite mastered some of those concepts, you need to really be sure that you do so. Whether that is through coming to my office hours and having a discussion with me and trying to bring you up to speed, or maybe setting up an appointment outside of that time frame. If those times don't work for you, email me and we can figure something out. Maybe going to a tutoring session with the Learning Commons. They're an incredible resource over there. They have some great tutors, and all of that tutoring is by Zoom for now as well. But you really do have to do something in order to make sure that you are able to do all the things that we talked about in Unit 1, because you will struggle with Unit 2 if you cannot. If you're still struggling with some of those conversions, if you're still struggling with some balancing and what that means, Unit 2 is going to be a struggle for you and things are going to keep building. And so I just wanted to be upfront and let everyone know about that. And so let's look at Unit 2. What we will be looking at Unit 2 are the amounts. Two big concepts that'll form our lectures are the amounts involved in chemical reactions. And so now we'll start doing things like saying that we're going to start with a certain amount of reactant and how much product are we going to make from that, and a lot of the differences and nuances involved in those sorts of calculations. The second major part of Unit 2 is we're going to start to look at energy changes, and we're going to start to look in detail at the amount of energy involved in both physical and chemical changes. And so calculating how much energy it might take in order to melt an ice block, or the amount of energy that is given off during a combustion reaction, things like that. And so those are our two major concepts in Unit 2. So the first 4 lectures, these first couple of weeks, are going to focus on the amounts involved in chemical reactions. And overall, that is a subject called stoichiometry. I know that looks like a big, scary word, and a lot of people stumble with saying that at first, but that's how you pronounce it, stoichiometry. And we're going to be using sort of this flowchart and this pathway here. We'll talk a fair bit about this as we move through this section of the unit. But one thing that I do want to point out to start out is you'll see what is central in this whole flowchart is the number of moles. Keep that in mind as we move through this stoichiometry section, that pretty much everything we do is going to flow through the number of moles. And so we need to be able to calculate how many moles there are of a certain given substance. So looking ahead just at the 4 lectures that we will be 4 lectures that we'll be covering stoichiometry. We're going to start today just by talking about the basics of it and looking at some of the mass relationships involved in chemical reactions. Lecture 2, we're going to go on and talk about something called limiting reactant, where one of the reactants is actually will limit how much product we can make. It sort of controls how much product we make. We'll talk about something called the percent yield in lecture 2. Lecture 3, we're going to start to really put some of this to work and look at various chemical analyses that can be done using some stoichiometric principles. And then finally, in lecture 4 for stoichiometry, we're going to be focusing in on a lot of stoichiometry that is involved with solutions. And so we'll see what all that means as we get there. So today, let's go ahead and start talking about some of the mass relationships that are involved in chemical reactions. So the basic study of mass relationships in general, or the basic study of the amount of things involved in chemical reactions, is called stoichiometry. What stoichiometry will do for us is it will start to provide for us quantitative information about reactions. So far, we've just talked about reactions qualitatively. We've said, okay, we're going to take some of reactant B, reactant A, and reactant B. We're going to mix them together, and we're going to get products C and D out from that. We haven't talked about anything involving the amount of product that we're going to get or the amount of reactants that we need. That's what the study of stoichiometry is all about. Stoichiometry as well, at its heart, centers around the law of conservation of mass, or the law of conservation of matter, which tells us that mass must be conserved in a chemical reaction. And so the total mass of the reactants that we have must be equal to the total mass of products. And so chemical equations must be sort of what we call balanced for mass. And we'll see what that is all about as we get a little further. Remember the balancing equations that we did? That's all tied into this. And so we call those those coefficients that we worked with when we put like a 2 in front of a reactant to balance it, something like that. We call those also stoichiometric coefficients, or we call the ratio within that balancing the stoichiometric ratio. And so if, for instance, and we'll see in much more detail what this really means, but if, for instance, there we go, we had just some general reaction, you know, maybe 2A plus 3B maybe just some sort of equation like this, then these numbers in front, the fact that it takes 2 of A and 3 of B, we call this a stoichiometric ratio. And we're going to be working with these ratios a lot throughout this whole entire unit on stoichiometry. And so those coefficients, then, they give us that ratio of reactants and products. As we'll see, what this ratio really is nothing more than a conversion factor. And we'll see what that means as we go through some of this. And so, for example, let's take a look at, and sort of, we'll just start thinking about how we're going to start thinking about reactions. If we look at just this example of this reaction here, just the combustion of methane, we have our CH4 plus a couple of O2s, end up giving us 1 CO2 and 2 H2Os. So far, the way that we have thought about reactions is thinking of it in terms of just single molecules. And so we've thought of this as one molecule of CH4, so one little CH4 molecule, has to react with 2 oxygen molecules. And through that process, 1 carbon dioxide molecule and 2 water molecules are formed. Because that's how we've thought of things so far. When we're looking at mass relationships, though, and the amounts involved in chemical reactions, thinking in terms of molecules really doesn't do us any good. Remember, because they're so tiny. And so we never have just 1 molecule and 2 molecules coming together. It's tons and tons and tons. It's lots of these molecules that are going to be reacting. And so we need to build that up. And so if we just see this first question here, how many molecules of water are produced when 1 molecule of CH4 reacts? So if I have 1 molecule of CH4, we can see then that from our balanced chemical equation, 1 molecule of this is going to make 2 molecules of H2O. So that's how we've talked about things so far. Well, what if we scale that up a little bit? If we say that we have a dozen molecules of CH4, so we have 1 dozen molecules of this, then it stands to reason, just given our balanced chemical equation, it stands to reason if I have 1 dozen molecules of this, then I'm going to make 2 dozen molecules of this. All right, because we see that they react in a 1-to-2 ratio. 1 of these gives 2 of these. So a dozen of these is going to give 2 dozen of these. Well, now we're just going to scale that up even more. We're going to think in terms of the number of moles. So remember that moles are just a counting unit, just like a dozen, just a heck of a lot more and a lot bigger. And so if I have 1 mole of CH4, then it stands to reason I'm going to produce 2 moles of H2O. What if I have 2 moles of CH4? Then I'm going to produce 4 moles of H2O, right? Because it's a 1-to-2 ratio. For every 1 CH4 that I have, I'm going to make 2 H2Os. So if I have 2 moles of CH4, then I'm going to make 4 moles of H2O. And it's that conversion which lies at the heart of what we're going to discuss with this whole stoichiometry unit. And so if we take a look at this example, so we want to know for this equation, how many moles of water are produced if 3 moles of oxygen react. And so one way to think about this, one way to think about sort of stoichiometry in general, and when we look at our balanced chemical equation, think of these like a recipe. And so in this recipe, we're given our general ratios. We're told that for every 2 ethanes that we have, every 2 C2H6, we need 7 oxygens, and that's going to give us 4 CO2s and 6 H2Os. And so that's our general overall recipe for this reaction. What we're saying here now with this question is if I actually only have 3 moles of oxygen, then how much water do I produce? And so this would be sort of like, I mean, if I give an example of maybe I've got some generic cookie recipe, and in the recipe, I'm given something like the recipe calls for 1 entire bag of chocolate chips. And so then the other features in that recipe are the ratio if I have a whole bag of chocolate chips. But instead I'm saying, okay, instead of a whole bag, maybe I've only got half a bag of chocolate chips. So how many cookies can I make? And so if in the recipe that 1 bag of chocolate chips can make 30 cookies, then we're saying, okay, well, if I only have half a bag of chocolate chips, then I'm only going to make 15 cookies because of the ratio of my chocolate chips to how many cookies I can produce. So same thing here. Our equation gives us our basic ratio, gives us our basic recipe. But then we're going to say, okay, well, using that ratio based on how much I actually have, how much am I going to be able to form? And so we're going to use those stoichiometric coefficients, which are conversion factors, allowing us to convert between one or the other. So let's look at how we would do that here. So here we want to go from moles of H2O, so from moles of O2, we're given 3.0 moles of oxygen. So we're going to go from moles of O2 to moles of H2O. So that's our starting information, is our 3.0 moles of O2. And then we just use our conversion factor from our balanced chemical equation. We know that we would make 6 H2Os from 7 O2s. So there's our conversion factor right there. There's our conversion factor for going back and forth between moles of oxygen and moles of H2O. And so then we would set this up. So we would have 3 times 6 divided by 7, and we would discover that that's 2.6 moles of H2O. And so if I have 3.0 moles of oxygen, I'm going to be able to form 2.6 moles of water. Again, we can see how that cancels out. Now note here, as far as your significant digits, we have 2 significant digits in our initial information, 3.0 moles of oxygen. Our conversion factor is exact, and so that's considered an exact number. It's a counted number, really. So since that is an exact conversion factor, it does not factor into our significant figures. And so we're going to use our measurement in order to, in the initial number we were given, for what determines our sig figs. And so 2 sig figs in our initial amount here, and so our answer is going to have 2 sig figs. So let's look a little bit more at those conversion factors, at that stoichiometric ratio. So in this example, iodine and fluorine are going to react to form iodine trifluoride. First thing we have to do is write the equation for this. We have to be able to write out our balanced chemical equation for this particular reaction. So there's our first step. And so we know that both iodine and fluorine are diatomic molecules. And so when they react, they will do so in the form of I2 plus F2. And we're told that those react to form iodine trifluoride, so IF3. But now we need to balance this. This is clearly not a balanced equation as written, and so we need to go through and balance this equation. When we do so, we get I2 plus 3F2 react to give us 2 IF3s. So now let's look at all the different stoichiometric ratios, the stoichiometric conversions that we have with this particular equation. And so 1 I2 would relate to 3 F2s, right? In this particular reaction, for every 1 I2 that I have, I'm going to need 3 F2s. For every 1 I2 that I have, I'm going to make 2 IF3s. And I'm just pulling that right from our chemical equation, 1 I2 to 2 IF3s. Finally, our other one, relating our F2 and our IF3, 3 F2s is going to relate to 2 IF3s. And so these are each conversion factors that we can use depending on what we're converting, depending on what information we're given and what information we might be looking for. Now remember, one of the keys with conversion factors is that they can be written either way. This is huge for us for this unit. And so we could either write 1 mole of I2 to 3 moles of F2, if we're looking at our first relationship here. So 1 mole of I2 to 3 moles of F2, or 3 moles of F2 to 1 mole of I2. And we would simply use that conversion factor in whatever form we needed, depending on what information we had and what we were looking for. So remember, back to our conversation about dimensional analysis in the last unit, this is the same thing as saying that I can either think of 60 seconds in 1 hour, or 1 hour has 60 seconds. And so I would think of that conversion differently depending which direction I was converting. Same idea here. We're going to use our conversion factors from our stoichiometric ratios in whatever way we need so that we actually end up with what we're looking for. And so in this example here, how many moles of I2 are needed to form 4 moles of IF3? Now, this is something that you can hopefully just sort of figure out looking at it, but let's go through a dimensional analysis setup for this and how we would actually set this up in a problem. And so we are given 4 moles of IF3. That's what we're looking for. So that's the information that we're given here. And so we're looking for I2. And so we're equating these two. We're equating our I2 and our IF3. And so we know that it's 1 mole of I2 to 2 moles of IF3. And so then the question is, how do we set that up as a conversion factor so that moles of IF3 will cancel out and we'll be left with moles of I2, since that's what we're looking for. And so we can see that we have to set up our conversion factor just like this. So that IF3 will now cancel out and we'd be left with moles of I2. And so we can see that we would need, mouse is acting up today, we would need 2 moles of I2. Here we want to know how many moles of F2 are needed to produce 12 moles of IF3. And so now we're equating our F2 and our IF3. And so we can see that for every 3 moles of F2 that I have, I produce 2 moles of IF3. So again, it's a question of how do I set that conversion factor up? so that my IF3 cancels out, since that's what I have to begin with, and I end up with moles of F2, which is what I'm looking for. Oop, went backwards. And so here's our 12 moles of IF3, our starting information. And then I want my conversion factor set up like this, 3 moles of F2 up top, so I'll be left with that. My 2 moles of IF3 down bottom, so that my 2 moles of IF3 cancel out, or sorry, that my moles of IF3 cancel out. 12 times 3 divided by 2 gives me 18 moles of F2. And so I would need to have 18 moles of F2 in order to produce 12 moles of IF3. Now, you'll note here as well, and this will become big for us as we move through through this unit 2, you'll note that my stoichiometric ratio here is simply taken from my balanced chemical equation. It's completely independent of the amount that I actually have. I started with 12 moles, or I'm ending with 12 moles, but that's my given information, is 12 moles of IF3. And so that 12 moles does not come into play at all in my conversion factor here. This conversion factor is simply dependent on my balanced chemical equation. Similarly, again, think of it like a recipe. The ratio of ingredients that you need in order to bake some delicious cookies, that ratio in the recipe is independent of how much you actually have or how much you actually want to make. You're going to use them in conjunction with each other, certainly. But the actual amount that you have does not change what the ratio is of ingredients that you need. And that's a big idea for us that a lot of students get hung up on with some of the later calculations that we look at. So keep that distinction in mind. And so here's a last example. So we want to know how many moles of I2 that we need to react with 1.5 moles of F2. Oops, sorry, gave it away. And so we're looking now at our relationship between I2 and F2. So we have 1 I2 to 3 moles of F2. And so we have to figure out how to set up our conversion factor in order to end up with moles of I2. So that 1 mole of I2 goes on top. There's our 1 mole of I2 to 3 moles of F2. So that moles of F2 cancel out. So 1.5 divided by 3. And I end up with 0.5 moles of I2. And so that's how we're going to use these conversion factors. That's how we're going to use our stoichiometric ratios to convert back and forth from one thing in the reaction to another thing in the reaction. And you'll note here that when we went through these, that we can equate any two things in a reaction. We equated one of the reactants to the product, we equated the other reactant to the product, and we equated two of the reactants together. Let's say that there was a second product. If we had like A plus B makes C plus D, there's no reason that I couldn't relate C and D together. There's no reason I couldn't say, well, if I make so much of D, how much C did I also make? And so you don't get, another thing that students tend to do when we see some of the problems we're going to see in a little bit, is they tend to get caught in the trap of thinking that these problems are all going to be reactant and product, and that those are the things that we're always relating. You can go any direction with these stoichiometric problems that we talk about. And so keep that in mind, is that these ratios can be used to equate any two things in the reaction. And so let's look at our general pathway that we're going to take with some of these mass relationship problems. And so a very typical problem might be, I have so many, or I have a particular reaction, and reactant A is going to form product B. And you might be told you have 7 grams of reactant A, and you want to know how much of product B that's actually going to form. As you can see here, that direct calculation isn't possible. We can't simply say that I've got so much of reactant A, and so I'm going to make so much of reactant B. We can't go directly like that. There might very well be another reactant involved. There might be another product involved. There's other factors involved that don't allow us to directly relate grams of a reactant to grams of product. What we can do, however, as we just looked at, we can directly relate our number of moles. And that's what those stoichiometric ratios are all about. is comparing the number of moles of two things within a chemical reaction. That we can do. And so what we need to do first in a problem like this is take our grams of reactant A and use our molar mass to convert to moles of reactant A. We can then use our stoichiometric ratios that we just talked about to figure out how many moles of our product that's actually going to form. And then we can use the molar mass of B to then convert that over to grams. And that's a very, very common pathway that we're going to take in these problems. Note that moles are central to these calculations. For all of these different calculations that we do, they're going to go through moles in one way or another. Maybe you're given mass and you need to use molar mass to convert to moles. Maybe you'll be given the number of particles, and so you'll use Avogadro's number to convert to moles. Whatever it might be, all of these calculations are going to somehow go through the number of moles. And so that is our key to these questions. And so again, this sort of being a very common pathway, a very common type of problem, given the mass of one compound within the equation, find the mass of another compound. And so we would use our molar mass. This is sort of the same stuff we talked about on the other slide, just another way to look at it. We're going to use our molar mass of the first compound to convert to moles of that compound. We're then going to use the mole ratio, our stoichiometric coefficients, to convert to moles of the other compound. And then the molar mass of that new compound, compound 2, use the molar mass to go from moles to grams. And so this is an expression that I heard from, I believe it was Dr. Benedict a couple of years ago. If you're sitting there as we do some of these stoichiometry problems throughout this whole section, this next couple of weeks, if you're sitting there looking at a problem and you're saying to yourself, I don't even know where to start. I don't even know where the heck to begin with this. When in doubt, mole it out. If you don't even know where to begin, you're looking at a problem and you're saying to yourself, I have no idea what I'm doing here. I have no idea where to start. Try that as your first step. Whatever given amount that you have, whatever your given amount of a substance is, find a way to convert that to moles. If you have the grams, then just use your molar mass. If you have the number of particles, use Avogadro's number. We're going to talk about something called molarity in a little bit. So if you have the molarity and the volume, use that to find your moles. Whatever you need to do, figure out a way to convert your given amount to moles and then go from there. So let's look at an example. So here again is our combustion of methane. We've already looked at this reaction a few minutes ago. But here we have our CH4, our one molecule of methane, or our 1 mole of methane, reacts with 2 moles of O2 to give us 1 mole of carbon dioxide and 2 moles of water. And so we want to know a couple things. We want to know if I have 8.32 grams of methane, how much oxygen is actually used. And with that same 8.32 grams of methane, how much CO2 and H2O are going to form. And so we want to take our given amount of grams of methane and figure out what the mass is going to be of our other reactant, what the mass needs to be of our other reactant, and what the mass is of our 2 products that are formed. So let's go through the first one together. And so here's our balanced chemical equation. The first thing that we're going to do is use our molar mass to convert to moles of the given material. And so we were given 8.32 grams of CH4. We're going to use our molar mass. We find the molar mass. And then we use that to calculate that we start with 0.52 moles of CH4. So I'm just using my molar mass here to go from grams to moles. Then I can now use my molar ratio to convert to moles of the thing that I'm actually looking for. And so in the first example, we wanted to go to the number of grams of O2. So I'm going to use my molar ratio of 1 CH4 to 2 O2s to convert to moles of O2. And I just need to make sure that I set that up in the right way so my moles of CH4 cancel out, and I'm left with my moles of O2. So I'm going to take that 0.52 moles of CH4 times 2 moles of O2 divided by 1 mole of CH4, so my moles of CH4 cancel out. And so that tells me that I would need 1.04 moles of O2. And then finally, my last step. Now I'm sitting here with moles of O2, but that doesn't do me much good. I want grams of O2. And so I'm just going to use my molar mass of O2 now to convert that to grams of O2, 33.2. Oh, sorry, 33.3. And so those are the 3 steps that we just talked about, are 3 steps for this sort of basic pathway. Now you could certainly do all these 3 steps one after the other, just like I've shown here. I do want to show you, though, that you can also set this up in just one dimensional analysis string. And so we started with our 8.32 grams of CH4. Now, quite often, I don't know if you've seen me do this yet, but quite often when I do dimensional analysis, I set up sort of this little box, or I used to call it a train track technique. So I've got my 8.32 grams of CH4. First thing I need to do is to convert to moles of CH4. So I'm going to use my molar mass to do that. So 16.04 grams of CH4 to 1 mole of CH4. You'll notice that in quite often, just when I'm doing dimensional analysis, I will quite often write in the thing that I want to cancel out first, make sure that I get that in the correct box. Then I'll write in the other portion. So now there's step 1. Now I'm going to use my mole ratio just from my balanced equation. So 1 mole of CH4 to 2 moles of O2. And then my final step, now converting to grams of O2. 1 mole of O2 to 32.0 grams of O2. Couple notes here, just before we look at the final math of it, is, for one thing, note that sort of just like I was talking about with our recipe earlier and our ratios, the molar mass here, it doesn't matter what this ratio is. This ratio simply comes from our balanced chemical equation. This molar mass is independent of that. All we're doing here is we're going from moles of O2 to grams of O2. We just use our molar mass for that. What sometimes some students are tempted to do is put this 2 down here as well, but this 2 is simply coming from the reaction that we're working with. It is independent of what the actual molar mass is. So this step here is just the molar mass of O2. It does not matter what my ratio is here. I'm just using my molar mass of O2. You'll also note just how particular I was about writing not just 8.32 grams, but grams of CH4. In my molar mass conversion, grams of CH4 and moles of CH4. Moles of CH4, moles of O2, grams of O2, moles of O2. If you stay that particular with things, if you're that careful about writing out all of your units as we talk about stoichiometry, you will be doing yourself a favor, because these are going to get even a little bit longer and more complicated than what we see here. And so the more careful you are about writing all of your units, the more you're going to be able to keep track of things as you go. And taking those extra few seconds is just a huge organizational tip for you. And so then when we look at our final dimensional analysis setup, we're going to take everything up top. So 8.32 times 1 times 1 times 32.0. And then divided by everything down bottom, 16.04. And in this case, just times 1 times 1. Well, we do out the math for that, and it should be the same answer we had before, 33.3 grams of O2. So we can do the whole thing just in, there we go. We can do the whole thing just in one long dimensional analysis setup. And so either way you did it is perfectly fine. If you do the 3 separate steps and just keep track of the numbers along the way, or if you do just one-dimensional analysis setup, you're going to get to the same answer. Personally, for me, I always do the one-dimensional analysis setup like this, but that's what works for me. That might not be what works for you. And so take this same approach and try to figure out the other two. Try to calculate how much CO2 actually forms and how much H2O actually forms. Again, with starting from the starting amount of 8.32 grams of CH4. So go ahead and stop the video now and try those calculations and see what you can get. Hopefully what you got was 22.9 grams of CO2 and 18.7 grams of H2O. Let's take a look at another example. So in this example here, we have the reaction of aqueous calcium nitrate and aqueous sodium phosphate. They're going to react to form calcium phosphate, which will be a precipitate, and then some aqueous sodium nitrate. And so if we start the reaction by dissolving 3.87 grams of sodium nitrate and react this with an excess of sodium phosphate, and we'll talk more about what we mean by excess later in the next lecture, but essentially that just means that we're definitely adding enough sodium phosphate so that all of the calcium nitrate reacts. And so if we're starting with our 3.87 grams of calcium nitrate, how much calcium phosphate is going to form? And so this is another one. Go ahead and pause the video now and see what you can come up with, but you have the molar masses that you're going to need down below. So pause the video and see what you can come up with for the amount of calcium phosphate that will form. Hopefully you were able to come up with something. I actually haven't done this one out yet, so let's go ahead and look at what my setup was, or what my setup would be. Quite a bit of room to work with this one. So we're starting with 3.87 grams of our calcium nitrate. And so our first step is we need to convert that over to moles. And so we're going to use our molar mass of our calcium nitrate, 164.09. Then we're going to use our molar ratio from our balanced chemical equation. And so it's 3 moles of calcium nitrate. And we're looking for calcium phosphate. Sorry, and that's 1 mole of that from our equation. Then finally, we're going to use our molar mass of calcium phosphate, 310.18 grams of calcium phosphate per, and I'm running out of room. And so then we put that into our calculator. So I'm just gonna, I always just put the whole thing in at once. I'm gonna go 3.87 times 310.18. I'm just clearing things out. 3.87 times 310.18. Sorry, 87. Wow, my monkey thumbs are having trouble on the calculator today. 3.87 times 310.18 divided by 164.09 times 3. And so I literally put all that in at once on my calculator. So just and I can't, the screen shifted, so I can't show you the actual screen from the calculator. But just to show you how I actually input this, I just went 3.87 times 310.18 divided by 164.09 times 3. And so that's literally what I input into my calculator. Gives us a result of 2.44 grams of calcium phosphate. So hopefully that's what you got. But you can see again that we're taking that same basic pathway. Our first step, and so our step 1 right here is where we are going from grams of the calcium nitrate to moles of calcium nitrate. So there's our first step. Step 2, now we're using our balanced chemical equation to go to moles of the calcium phosphate. Step 3, from moles of calcium phosphate to grams of calcium phosphate. And so it's that same basic pathway. So our first step over to moles, our second step using our balanced chemical equation, the stoichiometric ratio, and then our last step finally then going to grams of the thing that we were looking for. Now, another thing to introduce quickly, this is something that you're going to use quite a bit in lecture coming up as well, and we're going to talk more about molarity later on, but I want to introduce it right now. Molarity is a measure of the concentration of a solution. And so if we have an aqueous solution, it's a measure of how many moles of the solute. So solute being the thing that is dissolved. Quite often that would be the solid that we're dissolving in water to make our solution, for instance. So how many moles of that solute are in 1 liter of the solution. So per volume of the solution, and by definition for molarity, that volume is 1 liter. And so that's our basic concentration unit that we're going to use in this class, is units of molarity. It's the moles per liter. And so that's one of the big thing to key on for molarity, is those are the units, moles per liter. You'll notice that's just another conversion factor. Moles per liter, just another conversion factor that we're going to use to convert back and forth between moles and liters. And so let's say, for instance, you're told that you have a 0.52 molar solution of, let's say just maybe NaCl. So it's a solution of NaCl. We know that the ions separate and all that we've talked about. That big M, that stands for molar. So it's a 0.52 molar solution. And what this really means is that it's 0.52 moles of NaCl per 1 liter. And that's how we would use it. And so it's just another conversion factor. Then we would use it like this. Maybe if we were given the liters and we wanted to find the number of moles. So if we were told, for instance, that we had 2 liters of solution, and we want to know how many moles of solution that is, then we're going to use a conversion factor just like this. And we're going to see that is 1.04. Then using the right number of sig figs, 1.0 moles of my NaCl. Or let's say you're told that you have the number of moles. Let's say you're told that you have 0.26 moles of NaCl with this solution. You want to know how many liters that is. Then we're going to use our conversion factor just the other way. So that moles of NaCl cancels out and I'd be left with liters. And I would see that this is 0.50 liters of solution. And so that's all molarity is. It's just another conversion factor. But those are your units, and that is very key for us, that the units of molarity are moles per liter. And so we'll be using that quite often. And so you might remember when I showed this graphic during our conversation in Unit 1 about number of moles and moles to grams and molar mass. And I included molarity with that at that point, and said it was something that we're going to be coming to. And here it is. Now we're there. And so molarity is just another way for us to get to the number of moles. We would use molarity if we were given the volume of an aqueous solution. And so if we're given that volume of an aqueous solution, then we're then going to multiply our molarity by that volume, which would get us to the number of moles, just like I did here. I needed to get to the number of moles in the first one. And so I took my volume, my 2 liters, I multiplied that by my molarity in order to get to my number of moles of NaCl. And like I said, we'll work with molarity a little bit more. Actually, later on in this unit, we're going to look more at solutions and molarity and concentrations. But I wanted to introduce it now just to show that it is another way. It's just one more way that we get to the number of moles in any sort of stoichiometric problem. So just like in this pathway here, so what this pathway shows us is that if we're given any sort of amount of one thing in a reaction, we can use that to then get to any sort of amount of another thing in a reaction. But what we have to go through is that number of moles. And so let's say, for instance, sort of the examples that we looked at to start out, we were given a mass of one thing in the reaction, and we wanted to find the mass of another thing in the reaction. So what we did there is we took the mass and we used our molar mass to convert that to number of moles of that particular thing. We use that number of moles to then use our stoichiometric ratio to convert to moles of the thing that we were looking for, and then used our molar mass of that to convert it to mass. Let's say maybe you are given, in this case, let's say you're maybe given the volume of a pure substance. You're not given the mass, but maybe you're given the volume of something. You're told that you have 2.86 centimeters cubed of aluminum, and you want to know how much mass of something else that's going to make. Well, then you can use your density. We talked about density in Unit 1. We can use our density as a conversion factor to go from volume to mass, and then use our pathway. Let's say you're given the number of particles. Let's say you're told that you've got 7.2 times 10 to the 26th atoms of gold, and you want to know how much of something that's going to make. Okay, well then I'm going to use the number of particles, and I'm going to use Avogadro's number to get to the number of moles. Then I'm going to use my stoichiometric ratio, and I'm going to go wherever I need to from that. So let this flow chart here, let this sort of be a roadmap to you in completing, for instance, the practice problems that we're about to show. But any problem having to do with stoichiometry, allow this to be your roadmap and ask yourself, okay, what am I actually starting with? What type of amount am I starting with? You might even be given a problem where you're just told the number of moles, where you've got this many moles of reactant A, how much of B does that make? So now you're starting right here. And so whatever amount that you're given, figure out sort of where on this roadmap you are and what you need to use in order to get to moles of whatever it is that you're given in the problem. And then use your stoichiometric ratio to convert that to moles of whatever it is that you're looking for. And then take a look at whatever it is that you're actually asked for to find in the problem. Maybe you're asked to find the number of particles, so now you're going to use Avogadro's number. Maybe you're asked to find the molarity of a solution, so then you're going to take that number of moles and divide it by, sorry, you're going to use, maybe you're looking for a volume, is what I meant. If you're looking for a volume, you're going to take you're going to take that number of moles, and you're going to use the molarity to find a volume. If you're looking for a mass, you're going to use the molar mass, just like we've done. If you're ultimately looking for the volume of a pure substance, the volume of a solid, then you're going to use that mass and the density. And so allow this to be your roadmap and use it accordingly, depending on what you're given for information and what you're ultimately looking for. And so let's do several practice problems now. And so with these, what I'm going to do, actually, you might want to pause the video now, maybe just copy these down, because I'm going to shrink this down fairly small in just a second. So you might want to just, if you're going to hopefully do these along with me, is pause the video now and copy these so that I can bring up make this smaller and bring up another graphic. So do that if you want. Go ahead and pause the video now and copy these down. so that I can now do this. I'm just going to shrink this down. Do this. I want to bring up. So I'm going to bring up our pathway. Okay. And so we have our balanced chemical reaction up top. So we have our balanced equation here, and we're gonna look at several different calculations with that using our pathway above right here. So in the first question, if you begin with 2.63 grams of aluminum and an excess of our copper nitrate, how many atoms of copper will precipitate? And so we're given grams of aluminum. So we're starting right here. We're starting with a mass of A. And so we're going to go ahead and just use that. So our 2.63 grams of aluminum. And so our first step is to use the molar mass and convert that to moles of aluminum. And so aluminum, where are we? 26.98 grams of aluminum per 1 mole. So there's my first step. And I want to get to the number of atoms of copper. So now I'm going to use my molar ratio between aluminum and copper to convert to moles of copper. And so I've got, and from my balanced equation, 1 mole of aluminum to 3 moles of copper. So I'm just using my balanced equation here. 1 mole of aluminum to 3 moles of copper. And again, we see that I've set up my dimensional analysis setup so that my moles of aluminum are going to cancel out. And again, here my grams of aluminum canceled out. And so now I'm sitting right here in our roadmap on my moles of copper, but I want to get to the number of atoms of copper. So I'm going to use Avogadro's number to convert to the number of atoms of copper. So in 1 mole of copper, I would have 6.02 times 10 to the 23rd atoms of copper. So now I should be done. So we can see the way our units have canceled out. I've done everything that I would need to be left with atoms of copper. So I plug this in, 2.63 times 3 times 6.02 times 10 to the 23rd, all divided by 26.98. And I get 1.76 times 10 to the 23rd atoms of copper. And so you can see here, again, if we just followed the pathway, started here with my 2.63 grams of aluminum, use my molar mass to convert that to moles of aluminum, use my stoichiometric ratio to convert to moles of copper, and then I used Avogadro's number to convert to moles of copper, to convert to atoms of copper. Let's take a look at the next one. So here we're told that we're beginning with 575 milliliters of the copper 2 nitrate. So we're given a volume and a molarity of this solution. So 575 milliliters of my copper 2 nitrate. And so my first step is, so I'm starting now right here, my 575 milliliters, and I'm going to use my molarity to convert that to moles of copper nitrate. One thing we do have to recognize here, though, is that molarity, remember, is moles per liter. That's an M, believe it or not. And so we need to convert this milliliters over to liters before we can do anything. And so we're going to have 1,000 milliliters per 1 liter. Now I can use my molarity. 0.250 moles of copper nitrate per liter. Remember, those are the units of that molarity. That 0.250 molar is 0.250 moles per liter. I need liters to cancel out, so that's going to go down bottom. My 0.250 moles up top. I can see very quickly I am going to run out of space with this one, so we'll just continue down bottom. But so now I'm sitting right here. Now I've got my moles of my copper 2 nitrate. So now I'm going to use my stoichiometric ratio. I want to get to grams of copper. And so I'm going to use my 3:3 ratio here. So 3 moles of the copper nitrate to 3 moles of copper. Dot, 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 just to show that I'm going to continue that now down below. So this is just a continuation down here. And so now I'm sitting right here in my pathway. Now I'm sitting with moles of the thing that I'm looking for. And I want to know how many grams will actually form. So I'm going to use my molar mass, copper, 63.546. And if we look at the units, milliliters cancels out, liters cancels out, moles of copper nitrate cancels out, moles of copper cancels out. So I'd be left with grams of copper, which is what I'm looking for. So I get my 575 times 0.25 times 3 times 63.546, all divided by, what do I have down bottom? 1,000 times 3, leaving me with 9.1 grams of copper. Now, take note here that yes, this step here mathematically comes out to 1. So mathematically, no, I don't need that in there. But this is the crucial step. You want to make sure to still include this, because this is the crucial step where we are converting between moles of the thing that we're given and moles of the thing that we're looking for. And so that's this step right here. Even though mathematically that doesn't necessarily need to be in for this one, include that with your work, because that's the key step of how we're converting between one thing and another. So the last example that we have here, now we're beginning with 3.45 cms cubed of aluminum, and we're given the density, and we want to know how many grams of copper will precipitate. So now we're starting right here. Now we're starting with our volume of a pure solid. And so we're starting with 3.45 cms cubed of aluminum. And so we're going to go ahead and use our density first. 2.7 grams per centimeter squared cubed. 2.7 grams of aluminum per 1 cm cubed of aluminum. So we've done this step here. Now we know the mass of aluminum. So then we're going to use our molar mass to convert to moles of aluminum. 26.98. So now I know the moles of aluminum. Now I'm going to use my stoichiometric ratio to go from moles of aluminum to moles of copper. So I see that's a 1:3, 1 mole of aluminum to 3 moles of copper. But now, once again, I'm looking for how many atoms of copper are going to precipitate. So I'm going to use Avogadro's number, 6.02 times 10 to the 23rd atoms of copper per 1 mole of copper. CMs cubed cancels out, grams cancels out, moles of aluminum cancels out, moles of copper cancels out. I'd be left with atoms of copper. Plug this into my calculator. 3.45 times 3 times 6.02. 02 times 10 to the 23rd, all divided by just 26.98 at the bottom. 2.31 times 10 to the 23rd atoms of copper. And there we have it. And so there are several different examples of sort of how we use the stoichiometric pathway. And so, like I mentioned, though, I can just bring this back up to size. Oh, let's come back to here. And so with all of these stoichiometric problems that we do, like I mentioned, I can't say this enough, we have to go through moles. And so most of these problems are going to consist of you figuring out, with what I have for information, how do I get to moles? Then you'll use your stoichiometric ratio to convert to moles of the thing you're looking for. And then once again, figure out, okay, now I have moles of the thing that I was looking for. How do I convert that to whatever amount the question is asking me for? Do I use my molar mass to convert to mass? Do I use my molarity to convert to volume, and so forth? And so that is all for today. These are just some of the very basics of stoichiometry, the basics of some of these mass relationships. And so hopefully you're finding a couple things. One, the importance of dimensional analysis. We really start to use it a lot now. So hopefully that is something that you spent some time with and that you are comfortable with. And you're also seeing how much of the things that we did use in Unit 1 are now starting to build. We have to be able to balance equations. We have to be familiar with moles and our conversions involving moles and so forth. And so we really start to build up. And I also point that out just to really point out as well, that if you fall behind, hopefully you're starting to see that things are going to really start to snowball. And so this really is a class that you cannot afford to fall behind in. If you do, you will quickly find yourself buried. And so don't let things build up. Make sure that you're staying on top of things. Make sure you're getting in touch with me if you're not understanding something, or attending a tutoring session. Going to the LA sessions is a great way to make sure that you're staying up to speed as well. But that is all for today. Next time we will pick up by talking about things that might limit how much is actually formed. And so that's it. I hope everybody has a great day.